Okay, good morning, everyone. It's really my great pleasure to introduce our today's speaker, Professor Vincent Larson from University of Wisconsin. Well, I think most of you know Vince pretty well because he has been working with us in many years. So specifically during the period when we developed the next generation of atmospheric physics for our current version of ESRS version 3. Vince is well known for his pioneer work on CLAP, which is used to unify treatment of the shallow convection turbulence and the cloud macrophysics. He has played a key role in implementing and improving CLAP for Israel. Recently, he has developed an innovative tuning tool for Israel, which we will hear more in his today's talk. Once graduated from Yale University in 1992 and received his PhD in 1999 from MIT under Carrie Emanuel. After spending 2 years as a postdoc at CSU, he joined the University of Wisconsin uh, as a professor there since 2001. Without further ado, Vince, please begin.
Yeah, thank you so much, Chung, and thanks for giving me a slot to speak. I'll be talking about a poor man's tuner for expensive global models. This is work in collaboration with Jin Guo, Ben Stevens, Nils Wittfer, and Luis Hasenauer. So when we tune a model, we have two goals, or at least I have two goals. One is to tune away parametric error. In other words, I want to get a better answer. But also as a model developer, I want to get hints about what part of the model structure to change next. In other words, what part of the model is still wrong. And my hypothesis is the big gains in accuracy will come from improvements to model structure. So I just want to get the tuning over as quickly as possible so I can resume work on the model structure. But the problem is, how do we tune an expensive model? So screen simulations are expensive. Coupled ocean atmosphere simulations are expensive. So we can run short duration simulations, just 5-day simulations, and that will reduce the tuning time. But if we want to run long duration simulations, then running a perturbed parameter ensemble, or PPE, with hundreds of members is just too expensive. Okay, so then my talk will have three basic sections. One is I'll introduce this tuner, which we're calling QuadTune, and it uses a simple quadratic emulator. And the purpose of that is to reduce the number of global runs that we need to do. And then I'll show some example tuning results from EAM, which will give you a sense of the errors that you can get from this simple sort of emulator. And then I'll talk about two archetypal model errors, tuning trade-offs, and stubborn biases. Okay, so what's the basic idea? We take the globe and we carve it into 20 degree by 20 degree regions. This is just our standard configuration. And we sort of tile the globe and we choose a metric that we want to tune, that we want to match. So say shortwave cloud forcing. And then each value of shortwave cloud forcing in each tile is treated as a sample point, and we try and match the obs in each region by adjusting P parameter values. They could be from turbulence, or they could be from cloud microphysics or deep convection. So it's a standard sort of tuning problem, but we have regions. Okay, the recipe, the steps that we would follow are first, we choose our regional metrics. So for instance, shortwave cloud forcing in 20 by 20 degree regions, but we could choose custom regions if we want. We don't have to cover the whole globe. Then we choose our tuning parameters. That involves developer insight. And then we run two P+1 global simulations. So the one here corresponds to the default simulation. And then from that default, we perturb the parameters one at a time. So we take a parameter, we perturb it high, run a simulation, then we perturb it low, run another simulation, then set that parameter back to default, take the next parameter, perturb it high, perturb it low. So we end up with 2p plus 1 global simulations, and that's the part that's expensive. But I don't think I can get away with reducing this number of global simulations more, so that's what we're running now. And then once we have those global simulations, then we minimize the difference between the model and OBS and create some diagnostic plots. And that part's cheap. I can run that in a minute or two on a laptop computer. Okay, so just to get a sense of the tuning problem, let's compare it to linear regression, which is familiar. Now, QuadTune does quadratic regression, not linear regression, but linear regression is more familiar. So basically, we set up an equation like this where we choose some regions. So here I've chosen 3 regions, a stratocumulus, a cumulus, and a warm pool. And each region is given its own row in this matrix equation. The number and location of regions can be chosen flexibly. So if you got arm measurements at SGP, but ENA, and then TWP, and a bunch of other sites, well, if you want to have a new arm site, just add a new row. We have biases at each of those regions, which depend on the default model and the observations. We choose some parameters. Here we've chosen 2, P1 and P2, and we want to dot those into this sensitivity matrix in order to try and tune away these biases. So the sensitivity matrix, basically it's based on a Taylor series, and it's the sensitivity. So in the stratocumulus region, this element gives a sensitivity to P1, this element to P2. These are the sensitivities for the cumulus region, and so on. So we treat each row as a sample, like you might sample in statistics. Now you can kind of see why things might go awry. For instance, suppose this top row here is zeros. So in other words, in the stratocumulus region, there is no sensitivity to parameter P1 or P2. Then no matter how you tune these parameters, if you multiply them into this row, you're going to get 0. And if the bias is non-zero, well, you're never going to be able to match it. So that's a stubborn bias. We just need to choose another parameter which shows more sensitivity or make a change to the model structure. But there are other more complicated problems, such as tuning trade-offs. So imagine that this sensitivity row is non-zero, but it equals the cumulus row. So these 2 rows have the same sensitivities, but they have different biases. Say the stratocumulus is too dim and the cumulus is too bright. Well, then no matter how you tune these parameters, if you brighten the stratocumulus, you'll over-brighten the cumulus. And so it's a tuning trade-off. We're just stuck. Okay, so the point is you can kind of see the sensitivities that develop just by looking at the matrix equations. Now, QuadTune is a quadratic tuner. So all that means is we take our parameter dependence and we Taylor expand it. Our first term is just the sensitivities, and these are our parameters. But we also keep some quadratic terms, namely the diagonal ones. We omit the off-diagonal or interaction terms because that would require too many global simulations and we want to minimize the cost. And then our bias we just define as the default model simulation minus the OBS. We want the parameter dependence to match OBS, so we choose parameter values that do that. And then we end up with this sort of regression problem, which is like linear regression here, except we add in this sort of term which looks like kind of a regularizing term. It's quadratic. Now, one key thing to note is that there's no intercept in this problem. It's just we're fitting slopes here, not intercepts. That's just how the math comes out. Okay, now I'm advocating here, oh, just run 2p plus 1 simulations. We can't afford the cost. But if you can afford the cost and you do have a PPE just lying around, well, then definitely you should use it because that's going to give you a lot more information than a simple 2p plus 1 sort of emulator. But I would still argue that it may be helpful to try and fit a quadratic emulator to the PPE, which can be done, because that will aid the interpretability. So in other words, we don't want to just get a set of parameters from a PPE that are optimal. We want to understand how the PPE or how the tuner came up with those values, and in particular, what's preventing better values from being found, because that points us to the model structural error. So the goal here with the quadratic emulator is in part interpretability. So let me just give you some results so you get a sense of what can happen here. So this problem arose in the course of developing EAM version 3. So it was a version of the model on the way to version 3. Jen and I changed club. We made a modification to it, put it in, ran a simulation, and it didn't come out as well as we hoped. So then we decided, okay, let's retune. So we chose 5 club parameters, and we ran our 11 simulations, each lasting for 14 months. So it's not a huge computational burden. And we attempted to match shortwave cloud forcing over the whole globe. So this is what we started with. So this is our simulation, and the stratocumulus were just too bright. The shortwave cloud forcing was too strong as compared to OBS. And you can see in the bias plots it's just way too bright. And so our RMSE is sort of an unimpressive 12.66. And then after doing these 11 simulations, then we end up with this. So you can see there's still the error there, but it's better. You know, it's 10.4. And in comparison, this is Jun's hand tuning, which is even better. It's 10.1, and you can see the stratocumulus are dimmed further. But, you know, 11 simulations going from there to there isn't too bad. So this is sort of a typical, you know, error. This gives you the sense of how much you can expect from 2p+1 simulations. So now the question is, we want to figure out what's the model structural error, what's preventing QuadTune from doing better. And you can see that there are these blue regions where the solution has improved, but there are red regions where it's gotten worse. So there's one over Bolivia here and one over China here. There's 2 stratocumulus regions where it gets better. We want to understand why. So QuadTune, it will spit out a bunch of diagnostic plots, and this is one of them, and it just gives sort of an overview for situational awareness. So one of the problems with interpreting these tuning problems is that they're high dimensional. So if you have 5 parameters, we have 5 columns in our matrix, and that's just hard to visualize. So for this plot, what we did was we took each row and we calculated its magnitude. So we just took the overall sensitivity to all the parameters in some sense. And that reduces the problem to a one-dimensional problem that then we can plot on a scatter plot. And along the horizontal is sensitivity. So we have all 162 regions here. We've plotted them here. This is high sensitivity, so the favored stratocumulus region have very high sensitivity. And then on the vertical axis, we've plotted the bias. So these points are too bright down here, so the stratocumulus were too bright. And these points are too dim here. And then the way we can think about this is just the traditional way that we think about fitting a line to a cloud of scatter points. Again, we have no intercept. The intercept, so the line has to go through the origin. If we don't tune at all, then we're left with a horizontal line. Slope is 0. And that has big errors for the stratocumulus. So we can see just by looking at it that we can improve the fit by having a negative slope line that goes through the stratocumulus. But we can see it's not going to solve all the problems. So these points here are right on the y-axis. They have no sensitivity at all, and so they're unbudgeable. They're basically stubborn biases. No matter what we do, we're not going to improve those, and we can just see that immediately. So that's helpful. Then there are other regions which actually get worse. So some of these regions up here, if we use a negative slope line, they're actually pulled farther from the line than if we just left the line at the horizontal. So again, you can get an overview of what the tuner is trying to do, and it's going to try and fit the stratocumulus region at the expense of others. Okay, so zooming in further, let's suppose we want to know how individual parameters remove the biases. So this is another plot that QuadTune makes, and basically it takes our matrix equation and just visualizes it. So we have our equation here with the sensitivity matrix. We take our parameter and we multiply it into each row in order to get this, just in standard matrix multiplication. And then we just visualize it. So this top bar here is the top row of the matrix. The bias here is represented by the vertical black line. We want the bias to be 0, but it's not. It's huge. The clouds are way too bright. So then if we take the sum of the top row, then that's this horizontal bar black bar, that's telling us how far back we're getting towards zero. So QuadTune thinks it can remove most of the bias. Now, as we've seen, it's over optimistic, but nonetheless, that's what QuadTune thinks it can do. But how do the parameters contribute to that bias removal? Well, then we look at the individual terms. So this one parameter maybe represents this blue bar here, C8. This one represents that parameter there. And we can see that parameter is having a big influence, it's N2 thresh. And so we get a sense of which parameters really matter for which regions. Okay, so this is just another example of a plot that comes out of QuadTune. And the idea is if you have a simple emulator, it's easy to make these matrix equations and then just create visualizations. Okay, so archetypal model errors, tuning trade-offs, and stubborn biases. So let's just go through some examples. We mentioned one, which is Bolivia. That one got worse. Another was China. That one also got worse. So let me just show you briefly here the dashboard that QuadTune creates. So the Bolivian region is 615. So let's just look at that one. And okay, so that's this region here. These are the two favorite stratocumulus. They're being brought to zero, but this Bolivian region is too dim. And the tuning makes it even worse. It's being pulled farther from zero. But why? Okay, well, one thing we notice is that the parameter dependence for Bolivia here is very similar to the stratocumulus. So that green is like that green. That's one parameter, the surface parameter. That blue is like that blue. It's another parameter. You can see it's all about a factor of 2 different. So you can see, if we say N2 thresh, that's really pulling Bolivia too dim. Let's reduce it. Well, that parameter there, N2 thresh, I mean, that's also what's dimming the stratocumulus regions. If we, reduce that one down to 0, maybe that helped Bolivia, but then that hurts the stratocumulus. So you can see very clearly the tuning trade-off, and you can see the problem we have. You can also look in other plots, like the scatter plot. There's 615, it's up there. So you can see it's traded off. You pass a line through the stratocumulus, it's just going to make that one worse. So you get kind of a sense of what's going wrong. You can kind of then go back to the original plots and see things like, well, I tend to focus on the stratocumulus errors, but you notice over the Amazon it's quite red. And that, of course, I tend to forget about. And the tuner is reminding us that these parameters are not helping with that dimness over the Amazon. So maybe we should look at that. So the tuner kind of gives you a sense of where to look in order to help with these model structural errors. Okay, the other one, this is an interesting one, is over China. The results are quite untunable. So that's this one. You look at this region, and basically it's too dim, and then every single one of these parameter perturbations makes it worse. Like nothing is helping us pull it back towards 0. And so that's not good. And Jen said, wow, I think Club is just biased against China. And I said, Jen, look, we have to have a more scientific explanation. We can't just write that in a paper. And so we kind of looked at what the parameter dependence looks like, and it's pretty wild. So here's our parameters, C8, N2, surface, N2, thresh. Here's our region, China. The obs are this red line here. The default is this value 0.5. And this is what QuadTune shows, is this orange X here. But basically, if you perturb the parameter high, the result gets even worse. It gets even farther from the obs. If you perturb it low, it also gets worse. This one, the same thing. Perturb it high, perturb it low, they both get worse. And so I was like, wow, Jen's right. Club is biased against China. So this is very confusing and very complicated because the sensitivity actually changes sign. Like you can't analyze this with a simple sort of sensitivity analysis. And I confess I don't know what's going on here, but at least the QuadTune gives us a place to look, namely over the China region, and we can look at these sensitivity experiments at some point. So let me go back to the main talk here. One other thing, if I have a moment, which is QuadTune can also generate an ensemble of parameter sets. And the idea is to try to get a measure of uncertainty, and in particular, I'm interested in uncertainty due to model structural error rather than observational error, because I think in a future climate projection, it's probably model structural error that's going to lead to bad results as opposed to observations being bad. So how does QuadTune do that? Well, it tries to guesstimate the uncertainty due to model structural error by doing bootstrap sampling. So basically what it does is it takes all these regions, and instead of including all of them, it just samples from the 162 regions. Maybe it takes a sample from Australia, and then it replaces that. Maybe it takes another sample from Hawaii and replaces that, and then maybe chooses another sample, maybe from Hawaii again. And so you end up with this sample of squares, some of which are sampled twice, some of which are not sampled at all. And then you fit that to, you tune in order to find a parameter set. Then you resample again, tune, find another parameter set. And so you get a whole ensemble of parameter sets, each of which are tuning to slightly different regions and giving slightly different parameter sets. And my argument is that that's kind of akin to sampling the structural error in the sense that suppose the real function is this crazy curved red function, but our model is wrong. It's just a line that passes through the origin. So we have one parameter, m, the slope. If we tune to these 2 points, we get one slope. If we tune to the yellow 2 points, we get another slope. The spread in slopes depends on, or it reflects basically the change in slopes of this red line as we sample different regions. So we can follow that through with the bootstrap sampling, and we can see like in a future sort of scenario, maybe in the present day scenario, DICOM's region off the coast of California maybe doesn't show too much variance, doesn't show a lot of uncertainty, but strangely, in our future projections, it shows more uncertainty. So there's something about the future conditions which make that region more sensitive, the clouds more sensitive. Again, I don't understand that. I apologize, but I'm just trying to show here the method that we're pursuing. So in summary, what can we learn from QuadTune? One is we learn which regional biases involve trade-offs and which regions have stubborn biases. We learn when to give up. If the tuner doesn't yield acceptable results, then either we should find new parameters or reformulate the model structure. But also, and then we're working on this, is trying to estimate uncertainty with bootstrap sampling. So yeah, thanks for your time.